about. So Thomas is a regular visitor to Morocco. So they found this kind of structure, and this you see maybe the scale is on the nanometer scale. So this structure, I will come later to that. It's very similar to graphene. So this is hexagonal boron nitride, and that's the system I'm going to speak most about at the end of my talk. So they found this structure in experiments, and it's just they measured some properties. Again, this started at the same time as graphene. So you can see in the last 15 years, we have studied from these two-dimensional materials. The questions which are of concern here, of course, the two-dimensional materials, are they really stable to remain unreactive? So in the experiment, we do the experiments in computers, so we can calculate all kinds of structures. Whether they can be realized in experiments, it's left to the experiments, so the engineers. So the question is, we always have to be concerned if we calculate a two-dimensional material, can that really be stable? So that's one concern. Then usually we need the support. So you saw example yesterday, Brother Hamid Ougadou was speaking about silicene, and he always had it on support. So some material where this two-dimensional materials was laid on. There are some materials which are stable also in air, single layers. Of course, graphene is one of the examples. So far, we haven't found for example, silicene, which would be stable without the support. And then if we have support, does that affect also the periodicity or the properties of this two-dimensional material? That's, of course, one question. So then we have this interaction intra-layer. So the previous example of hexagon boron nitride, for example, the bonds in the layer are very strong. And usually the interaction from this two-dimensional layer to the substrate is much weaker. So now we have to find this balance. If we want that the support doesn't affect the properties of the overlayer, then of course this interaction of the layer to the support should be as weak as possible. And then we come to the description of the small or weak forces, like the van der Waals forces that Brother Gade was talking about. And then, of course, is the periodicity, is it affected, and then is the electron structure affected? Well, by now you have seen many examples of two-dimensional materials. Of course, it is started, so graphene, carbon, and the boron nitride. So you just take these. So first we had group 4 elements, so carbon, graphene. Then, like Hamid was talking yesterday about, silicon forming silicene, germanium, germanine, and tin. Just in the previous talk, we had a nice example of two-dimensional 3,5 material, and because of the polarity, it opens a gap. You saw that these materials, they had the gap, boron nitride. It was also mentioned by the previous speaker. So it also has a band gap. So it has the same structure otherwise, but because of the different electronegativity of boron and nitrogen, it opens a band gap. So there's no Dirac cone there. So, but we use it for different purposes. One of the purposes was also mentioned by the previous speaker. So it's about to insulate the material. We have almost a perfect insulator, weakly interacting and having a large band gap, so it doesn't affect the properties a lot. And then, of course, we have, for example, these transition metal dichalcogenides. I haven't seen a presentation so far. I'm not going to go into them, but of course, this is one of the materials that are of great interest today in the world of two-dimensional materials. There are many other examples. I'm not going to them, but let's see how far we get. So, Professor Gara was already talking about this. How to sample the methods used there. So we need to sample the phase space. So phase space means different positions, different velocities, for example at finite temperatures. Then of course the main methods of use, they are the Monte Carlo and molecular dynamics. Then what I will talk quickly mention other high-throughput methods and artificial intelligence, another code name for example, machine learning. So quickly about the high-throughput methods, I show one example also here. So nowadays, these calculations of electron structure, we can call them, they are basically black box. So basically, if you give the coordinates to a density functional code, for example, you most likely, if you have reasonable setup independent of these coordinates, you get something out. And that something out is quite usually reasonably accurate and reasonably reliable. At least we know the trends when the calculations work and we use those materials, then this is becoming a black box. So we have many codes. One of the examples is the quantum mesh peso, and there are other codes. So the idea of these high throughput methods is that, okay, we can let the computer do this job, and we can then launch many of those jobs. So we just need to give the computer something to crunch, some structures. They do it independently. We don't need to care about the convergence usually, and at the end they give rather reliable results, like was mentioned before. And so we can make lots of these calculations. So this is the high throughput. Some people will talk about this big data also. So now the question is, if you have let's say tens of thousands of calculations and you have to find then the results after a couple of weeks, at least I would forget completely which calculation was which. So the idea of this interface is like the one which is the activities led by Nicola Mazzari at Lausanne nowadays, is a code called AIDA. So the idea is that you can also create some networks which perform your calculations, like systematic calculations, and they also store the data in places where it's probably rather easy to find them. And this is, of course, thanks to the black box idea and the speed of the computer. So we can do plenty of calculations, and then we can leave the kind of bookkeeping to some applications, rather than trying to remember, okay, where are the results of the calculation I did 2 months ago. So this is one of the trends which has appeared. The big data is, of course, in many fields. And also this, during yesterday, today, I have seen several examples of using artificial intelligence in many fields, and now it's also popular in the field of atomistic simulations. So the idea is, it's kind of a fitting. We fit something like a force field or interaction between the atoms, which we can then use in these calculations. For example, molecular dynamics, it was mentioned before. So this most common approach to this is the machine learning, artificial intelligence. So we tell the computer how it will learn from the data that we give it, and this will give out then these parameterized force fields, for example. And the most used one of these methods of machine learning are the neural networks. I have also seen examples here. So this is basically the idea. Most of the implementations, they use this so-called deep learning neural networks. So this is the inputs. So we give some characteristic of the system, like distances between atoms and angles and so on. And then we have this output, and in between we have something which is totally a black box. Usually it has no physical meaning, it's just numerical functions. Some people criticize this approach that you don't put any physical inside here. It's just mathematical functions which have nothing to do with the physics of the system. But it has been shown now in several applications, there are more and more appearing, is that you can really use this approach. So first teaching this network how it behaves in your test systems, then you can maybe test it. So you see how accurate it is with some reference data, and then you use it in real applications. And the idea is that instead of doing all the calculations using the heavy machinery like density function theory, now this neural network evaluates the value of a given atomic configuration. It's much faster. It's orders of magnitude faster than if you would do the density functional calculation. So the idea is to increase the throughput by this kind of semi-automized fitting of new force fields or interaction between the atoms. So the computation kernel, we have heard many talks about DFT. Professor Kara mentioned the wave function based methods. There are also those which have appeared in the materials world. So there are some implementation of MP2, which is beyond Hartree-Fock in the wave function methods, couple clusters. So these have appeared also in the application of solids. And quantum Monte Carlo is another approach of methods. I haven't seen any presentations here, but it has, let's say in the 5 years, it has again become popular. And of course, the idea here is that in principle, we get to, again, towards the exact result. So there are some approximations, but they are different than in DFT. So probably complementing those, we get, or it's another way of going towards more and more realistic calculations. And also the computers are helping, so the computational power is increasing, so we get better and better results. So DFT, we can easily treat hundreds of atoms. Just with big supercomputers, maybe we can get to, let's say, 10,000 atoms. And yeah, we have reasonable accuracy. So like we discussed before, so often we know how accurate we expect, let's say, exchange correlation approximation to be. Of course, there's no proof. So quickly about optical properties, it was also mentioned during yesterday, today. So we could use hybrid functionals to get more accurate results than just a normal GGA, like Professor Gara was mentioning. And then some specialized functionals I wanted to mention. You don't see the details, it's just, there appeared just recently an article which compared some of those approaches. One of them is this modified Becker-Johnson approach, which I know also in Morocco it's often used. So it's a cheaper way than the hybrid functionals, and one gets, it's the red circle. So this one, if we would get the experimental bandgap with calculated bandgap, if it would be linear, that would of course be the ideal world. And the GGA is always, well, practically always below. Then this modified Becker-Johnson, it's pretty well on the diagonal. So this is, yeah, nice benchmark results recently in some materials. They also did some magnetic properties. So it appeared just recently. And then, of course, the real way, so if you really want accurate optical properties, the real way is the many-body methods like GW. Now the people are starting to go to the vertex corrections and self-consistency, and then to get the excitons, for example, the two-body properties, we need to go to the beta-Salpeter method. So maybe I very quickly mention the weak interactions. So in two-dimensional materials, many of them, so they are weakly interacting between the layers, of course, because otherwise they would be reactive and probably would not be stable. So Professor Gara was already mentioning that now we are relatively well handling, hopefully, the weak interactions roundabouts. So I will go quickly this because of time and because Professor Gara was mentioning that already. So I start now. Depending on the chairperson, I have probably something like 60 minutes left before we have to evacuate the room. So I will go through some applications, and I felt obliged actually to start with graphene, even if my title is Beyond Graphene. This is somehow beyond graphene, because what they do is, well, they talk about localized strong electric fields, but what they actually do, they shoot highly charged atoms, ions, through graphene, or some of the atoms, they bounce back, but what they do is they shoot highly ionized ions, and then they look what comes through in the experiment. And then they make conclusions about the results, and they have computational modeling. So the persons, I feel, yeah, obliged, because just 2 weeks ago I visited Fritz Aumeier here in Vienna, and he, well, forced me, of course, as an experimentalist to see the equipment, and then I got very interested in the results. So very quickly, the results, I'm not going to explain them, but basically what they do is, these are different ions of xenon and different energies. Of course, the higher the energy that they shoot xenon with, the more goes through. And so this is these are the peaks. So basically what comes through the single layer of graphene in the equipment. And what they conclude is that from this is that when the ion goes through, then it ionizes, of course, the graphene. But because the close region is strongly ionized, then the electrons from the graphene, they fill this hole of electrons very, very fast. And they concluded that it's something like 30, 35 electrons that they get very quickly. I mean, they ionize something like 30, 35 electrons. They take away the ion which is approaching. But it's very, very quickly compensated by the electrons in graphene. So this was the strong and localized electric field. So this was the ionization, quick ionization, and then the recovery. So they made conclusions, and they got some support from theorists. So this is just the ion approaching, and this shows the perpendicular and radial currents in these plots at different distances. So they did time-dependent DFT modeling, what happens as a function of time to the electrons when the ion is approaching. I'm not going into details. If you want, you can look at the original literature. I just wanted to show an application. The next application, this is about the group 4 elements and related to what Professor Hamidou Kaddourou showed yesterday. So these were the silicene and germanium, so single layer of silicon and germanium. This was a pure theoretical calculation, and this was, to my knowledge, the first DFT calculation where they also, like Hamid showed, they found that the layer would be buckled. Well, then it has two minima and so on, some details, but they, like Professor Gade yesterday mentioned in a presentation in our DFT workshop, I mean, they calculated and found that you have negative phonon frequency, which actually means that the system is unstable. It's actually imaginary frequency if the layer would be planar. And only when you get the buckling, you get all frequencies positive. So this was one of the cases where the calculations actually came earlier than, well, still there's no single layer silicene, but it was a very nice example of how you can do simple physics, 2 atoms in the unit cell. Then I want to mention, I showed some equations. This was not to scare you too much, just to remind you, when you go to more than one material in the unit cell, and if you go to the systems with a band gap, the calculations, they become slightly more involved, because you have to consider different charge states in your system. So your system, it's possible that it has the Fermi level somewhere in the band gap, and that where this Fermi level is, so the chemical potential of the electrons with respect to the valence band maximum, you can have different stable structures. So if you dope the system with electrons holes, you can get different charge states. So one has to consider those. And then, of course, if you have more than one type of atoms, then you should take into account also the chemical potential of the elements. So this then comes to the conditions of the growth of your sample. So, for example, if you have 2 elements in a system, previous system, indium and selenide, so then it depends on the growth conditions, basically, where the chemical potentials were during the growth. And then you should take that into account. Then possibly you also have to take into account the entropy and so on, but I don't have time to go. I just want to remind you that when you go to the more complex materials, the calculation of properties becomes more involved, because you have to take these different possible conditions of charge states and the chemical potential in account. Just an example, Kari Larsen and his co-workers recently studied the edges of the molybdenum disulfide nanostructure. So then, depending on the chemical potential, they calculated, and then depending on the chemical potential, some of these structures are stable at different values of the chemical potential. And they also studied the adsorption of hydrogen and then the effect of impurities. So this is iron on these molybdenum disulfides, one kind of edge, and then hydrogen. So they use the charge states, different charge states. So now coming back to the HBN chair, may I interrupt? How many minutes? 6 minutes. Okay, so I just go maybe 1 or 2 examples that have appeared in the literature. So again, reminding you the structure of HBN. So the bulk, there's also bulk HBN, but like in graphite, the interaction between the layers is very weak, so it's easy to, let's say, relatively easy to well, cut these layers. Well, usually on the surface, one uses a growth method. So one starts from a molecular precursor and then forms the two-dimensional layer. And this system, which I'm now showing, actually Oliver Kroning showed one example. So this system is the hexagon boron nitride on rhodium-111. So I only showed some example of molecule adsorption on the surface. So now I just show you how the system looks like in early calculations. So because of the different lattice constant of HBN and rhodium-111, actually this lattice constant doesn't match. And the system, I talked about it earlier, the HBN has a very strong intra-layer binding, so it doesn't want to change the lattice constant a lot. So what the system chooses is that I make a kind of quasi-commensurate structure, so that within 12 unit cells of the surface, I have 13 units of the HBN. And that leads to different adsorption sites of the boron and nitride within this unit cell of 12 by 12 surface atoms. And at some positions, you have a stronger binding to the substrate and somewhere the weaker one. So this leads to this corrugation. And the interaction is, we have seen in the calculations that the interaction is here at the strongly bound regions are the regions where the nitrogens are sitting just closest to the rhodium atoms. That is the solution why we see this corrugation, and the corrugation, as you saw in the first slides, was about 2 nanometers. So just now some examples, or maybe I will go and skip some of the systems because of the time. So this is, I just wanted to show, sorry, the title is wrong. So this is actually a single argon atom which was shot below the HBN layer on rhodium-111. So this is, Thomas Graeber wanted to call this nano tent. You see this looks like a tent on a rugged landscape. So what's then Marcello Iannucci did was, so this is, well, the title is actually, sorry, I have taken the wrong work, because they did also argon implantation beneath graphene and ruthenium, but this is actually argon below the HBN on rhodium-111. So this is what Marcello Iannucci did. She shot the argon atom in molecular dynamic simulation toward the surface, and I hope I managed to show the video. So this is the HBN, the substrate, and there's the argon atom. And here's the initial trajectory. So first it's a straight line, and when it comes to the HBN, it breaks the structure. I mean, this is of course to be expected. The argon comes with high energy. It doesn't have space, but its kinetic energy is sufficient to break some of the bonds. You see now that it just makes violence to the structure, and then what it does, it diffuses along the surface, and it ends up at this. I had to go back to the presentation. So it ends up at this region, so not below the pore, so where the atoms are closest, but where we have these regions of where there's more space below. So that's where the argon usually lands. That's also the case in this simulation. So the atom diffuses on the surface, and it finds then below these kind of hills in the structure. So this was one example where the simulations, molecular dynamic simulations, were combined with the experiments, again from the group of Jörg Osterwalder and Thomas Kreber in Zurich. And then I think I will finish my talk. Of course, I want to show some results from a nice collaboration that we had with Oliver Koenig when I was still in Zurich. So this is a similar molecule that Oliver showed in his talk, but this is actually a slightly smaller one. And then we have iodine atoms around it. So this is the molecule. So you see that if you would, so they're actually hydrogens. Sorry, well, I use this for the last few seconds. So you have hydrogen here. If you would replace those hydrogens with your carbon, so this would be a flake of graphene, similar to what Oliver was showing. And then we have iodine atoms here. And this is actually the similar recipe as Oliver showed for the creation of the graphene nanoribbons. It's easy on the surface to dissociate the iodine atoms, either by heating, by even with the tip of the STM. So one can remove those atoms. So this is the first adsorption structure, which actually looks very similar to what Oliver showed, even if it's a different molecule. So this is one image from the experiments. This is the adsorption structure from the calculations. And if one looks, we have 2 times of the, due to the symmetry of this kind of pore region and the adsorption structure, every second iodine atom is kind of at the site A, so I think it's this, this, and this, and every other one is kind of like structure B. And then these dissociation experiments, like I said, either by heating, one can dissociate these bonds. So here the iodine still stays in the pore. Here we have dissociated 2 of them. Oh, sorry, it's actually 3 of them. And then they can be also diffused away later in later stages of the experiment. And just showing this was then DFT calculations. We calculated the energy for breaking those bonds. So if we split the atoms from A, B, or A sites, or A sites, so these are the resulting structures, BBB or BAB, and we see basically, well, that the results, when we looked at the statistics from the experiment, they correlated with the statistics or the lowest energy dissociation reactions. So this is actually the dissociation product when we dissociated the DFT calculation and shows where the iodine will go. So this was again a nice agreement between the experimental theory. And more results from the collaboration with Oliver, with Macela Iannuzzi. So I wanted to give you just an overview of some of the methods, some of the trends, like this artificial intelligence, machine learning, neural networks, and then the high throughput methods, big data, and this really how they can be used to design also new materials. The examples I showed you, it was mostly on the hexagonal boron nitride, which can be used for this insulating layer. Like we saw the molecules of Oliver in his talk, or in what I presented here, they would interact strongly with metallic substrate, but because there's the HBN layer, the interaction is weaker. But still we can do some controlled reactions. Again, I repeat, maybe with the STM tip, one can select which atoms to break in the molecule. And now I would just end by saying that in the 2-dimensional materials, these computer simulations have a central role, both explaining and predicting new properties, new materials. And again, I leave it then to the experimentalists, engineers to finally try to synthesize those. So with this, I thank you for your attention.